Hi everyone. Today we're going to talk about section 16.4 Green's theorem. And before we do that, in fact, most if not all of this video is going to be spent on two concepts that I want to talk about before we actually get to Green's theorem. And they're called curl and divergence. So first, we assume that we have some three-dimensional vector field, F, and I'm going to call the components of that vector field P, Q, and R. We're going to assume that those component functions have continuous partial derivatives, and then we define the curl in this way. So the curl of F is another vector field that's defined as the partial derivative of R with respect to Y minus the partial derivative of Q with respect to Z. That's the first component. The second component is the partial derivative of P with respect to Z minus the partial derivative of R with respect to X. And the third component is the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y. Now, we're going to have a more intuitive way of computing this in a few minutes, so you don't have to actually memorize this. But a couple things to notice about curl. Curl is vector valued, so given a vector field, you take the curl, you get another vector field. And also, if you notice, these were the three conditions we had to check when we talked about conservative vector fields, that these three pairs were equal to each other. So that means if our vector field is conservative, then the curl is 0. So then the opposite, if the curl is 0, does that mean you have a conservative vector field? In order for that to be true, we have to assume all of those hypotheses we assumed when we talked about conservative vector fields, mainly that all of these partial derivatives are continuous on an open, simply connected domain. So if that's the case, in particular, if they're continuous on all of R3, then yes, if the curl is 0, you have a conservative vector field. Okay. So what does curl tell you? It measures how the vector field is making things rotate in general. I'm not a physicist, so I don't know a lot about the applications and the physical explanations of these things, but from my understanding, curl measures tendency for the vector field to cause things to rotate. Okay. If the curl is 0, then F is called irrotational. So conservative vector fields are irrotational. They don't rotate. So that's the first concept. The second concept is called divergence. And divergence is defined a little more simply. It's just the sum of these three partial derivatives, the partial derivative of the first component function with respect to x, plus the partial derivative of the second component function with respect to y, plus the partial derivative of the third component function with respect to z. Okay, and this gives you a scalar, so it's scalar valued, and it measures the amount that a vector field causes things to either expand or contract, expand or compress, move away or get closer, or you can think of it in terms of density. Divergence is measuring how a vector field is causing things to become either more or less dense. And if the density is constant, then the divergence is 0. Okay? If the divergence is 0, then F is called incompressible, right? Because you can't push things together or move things apart. Okay, so these are the two concepts, curl and divergence. These are how they're defined, but now let's look into an easier way to compute these things than just memorizing the definitions. And to do that, we're going to revisit the gradient. So when we talked about gradients, we had this triangle operator, had that in front of a function to denote a vector full of the partial derivatives of that function. So in 2 dimensions, partial derivatives of the same function with respect to x and y, in 3 dimensions, x, y, and z. So now we're actually going to give that triangle a name and call it the del operator. And the del operator is just an operator defined as a vector of these partial derivative operators. So here, this vector, there are no functions in here. These are just operators. When they act on a function, you take a partial derivative. So when this del operator acts on a function f, it gives you a gradient. Right? So we can think of the gradient as this del operator acting on a function. So if I want this to act on a function, I write f here. What happens is I take these partial derivatives of f, I put them in a vector, I get a gradient. Now, defining this as an operator gives us some convenient notation for curl and divergence. So the notation we use to define curl and divergence changes, but it also gives us a way to compute them. So what do I mean by that? I'm going to define curl now. I can write curl of f, but I'm also going to define the curl of f, the notation-wise, as this del operator crossed with our vector field f. So del cross f as a cross product. And so sometimes when people write curl, they write this. But also, this gives us a way to compute the curl, because I can actually work this out. So I set up my 3x3 determinant. My first row are the unit component vectors. Now my second row are the components of the del operator. So now these are operators. They're not functions, they're operators. And then the third row are the components of f. So now when I compute this cross product, usually when we do this, we multiply things together. But now it's not going to be multiplication, it's going to be an operator acting on a function. And so when the operator acts on the function, we take the derivative, because these are all derivative operators. So now when I compute this cross product, what happens? Well, I take the partial derivative of r with respect to y, and I subtract the partial derivative of q with respect to z, which I have here. The second component, I put a minus, and then I take the partial derivative of r with respect to x, subtract the partial derivative of p with respect to z, and then the third component, I take the partial derivative of q with respect to x and subtract the partial derivative of p with respect to y, and that's exactly how we defined the curl before. So it gives you a nice way to compute it using something you already know. Now, divergence is sometimes written as this del operator dotted with your vector field f. And then you can actually compute it that way. If I write out the del operator in this vector, I dot it with my vector field pqr. Then I compute this dot product with these operators acting on the functions. So I take the partial derivative of p with respect to x plus the partial derivative of q with respect to y plus the partial derivative of r with respect to z. That's exactly the divergence. And this is really convenient notation because we know that cross products give us vectors, and the curl is a vector, and here I'm writing it as a cross product. And we know that dot products give us scalars, and so we can write the divergence as a dot product, and the divergence is also a scalar. So it makes sense. It's kind of consistent. It's really nice notation. All right, let's do an example. So find the curl and divergence of this vector field x cubed y squared z I plus x squared zj plus x squared yk. So those are the three components of my vector field. If we find the curl first, I'm going to set up my 3x3 determinant. And now I'm going to take the partial derivative of x squared y with respect to y. That gives me x squared. The partial derivative of x squared z with respect to z gives me x squared. I subtract them. Then I put a minus. Take the partial derivative of x squared y with respect to x. That's 2xy. The partial derivative of x cubed y squared z with respect to z. That gives me x cubed y squared. And then the third component, I take the partial derivative of x squared z with respect to x to get 2xz, and then I subtract the partial derivative of x cubed y squared z with respect to y to get 2x cubed yz, and then I simplify. The first component is 0, and here I've simply distributed the negative. And I've got the curl. Now to take the divergence, it's a lot less work. I just need to calculate these three partial derivatives and add them together. So the partial derivative of the first component with respect to x is 3x squared y squared z. The partial derivative of the second component with respect to y is 0. Partial derivative of the third component with respect to z is 0. So then the divergence is just 3x squared y squared z. Okay. Now, for Green's theorem, in this section, we're only going to deal with two-dimensional vector fields. So divergence is defined exactly the same for two-dimensional vector fields. If I just scroll back up here, I just get rid of this partial derivative with respect to z, I get rid of this r, and so my divergence just has one less term in it. But cross products are only defined for three-dimensional vector fields. So the way we get around this is, if I have a two-dimensional vector field in the plane, then p and q are only going to be functions of x and y. There are going to be no z's in these functions. And I can say r is 0. So if I do that, and I start taking these partial derivatives, well, r is 0, so this partial derivative is 0. Q doesn't have any z's in it, So this partial derivative is 0. R is 0. P is just a function of x and y. There are no z's, so this is 0. So these first two components are 0. The only non-zero term I get involves the two components I have, and with partial derivatives with respect to x and y, the first two variables. So when I'm going to talk about curl for Green's theorem. This is all I'm going to talk about. In other words, we're just going to use the third component, or the kth component of curl. So it's not technically going to be the curl because curl should be a vector, but it's kind of a two-dimensional version of curl. It's the only non-zero, possibly non-zero part we could have for a two-dimensional vector field. Okay, before we go, I'd like to give some geometric interpretations of if you look at a vector field and just see a graph of a vector field, what can you say about its curl and divergence? Or can you get some intuition about the curl and divergence? And here I'm just going to talk about two-dimensional vector fields, not only because that's what we're going to deal with when we talk about Green's theorem, but also because they're easier to see when you plot them. So first, when we talk about curl, I'm going to say imagine that your two-dimensional vector field represents some flow of some fluid. Okay? And in this fluid, we're going to pretend that we drop a pencil. So you can think of a river and dropping a pencil in the river and seeing what happens to the pencil, assuming that it floats on the surface. Now, if the pencil spins counterclockwise, then this third component of curl, or this partial derivative of q with respect to x minus partial derivative of p with respect to y, is positive. If the pencil spins clockwise, then this component is negative, and if the pencil doesn't spin, then that component is 0. It's irrotational, right? So this is where the term irrotational comes from. The pencil doesn't spin, this is 0. If we look at a couple of examples of vector fields I have plotted here, here's the vector field negative yx, and you can see it's creating this kind of vortex here. If I were to drop a pencil into this, if this were described fluid flow and I drop a pencil in, this pencil is going to spin counterclockwise. And I've taken the curl here, and indeed the curl is 2, so it's positive. If I look at this next plot, and I imagine dropping a pencil in it, the pencil is going to turn this way, and down here it's going to turn this way, so it's going to start spinning clockwise, or at least moving in a clockwise manner. Even if I just keep the pencil in this top half, where things are only moving to the right, at the top things are moving to the right faster or more forcefully than at the bottom, so the pencil is still going to tilt in a clockwise manner. And so we would expect the curl to be negative here, and indeed it is. I take the curl, it's negative 1. In this third example, I have the vector field xy, and we can see this vector field is just pushing everything out from the middle. So if I were to put a pencil here, it wouldn't necessarily start rotating, it would just move outward. And so the curl here is 0. This is irrotational. Okay, now let's talk about a geometric interpretation of divergence. So for divergence, one way to think about this is to think that this vector field describes the flow of some gas. You could also think of a fluid, but fluids tend to be, at least water is what I tend to think of as incompressible. So it might be easier to think of a gas. So if the divergence is positive, then what's happening is the gas is dispersing. It's becoming less dense. The particles are moving away from each other. If the divergence is negative, that means the gas is compressing, or it's becoming more dense. All the particles are moving towards each other. And if the divergence is 0, then neither of those things are happening. So the particles are basically staying the same distance away from each other, and it's incompressible. So if we look at some examples or some plots of vector fields and look at their divergence, if we just start with this same vector field here, everything's moving away from each other, moving away from the center, so its divergence should be positive, and it is. The divergence here is 2. If I look at another vector field, everything's kind of going towards the center, so I would think the divergence here would be negative, and it is. It's negative 5. And if I look at this vector field again, where everything was just rotating, here I'm rotating counterclockwise, but things aren't really getting closer to each other or further apart from each other. They're just kind of traveling along these concentric circles. So the divergence here is 0. Okay. That's it for curl and divergence. In the next part of section 16.4, we'll actually talk about Green's theorem.